Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Diagramming capacitors in circuits simplified. Now, a capacitor, if you recall, is like a thin plate, right, connected in some kind of a circuit, and it gets a charge. So this gets a positive charge, and this gets a negative charge. It'd be connected somehow, with a power source, and then the charge dissipates. All right. So that's what a capacitor is, right? And then a note here when we're talking about that before I go to parallel is the symbol for a capacitor is two parallel things. Like I said that in a line. You might have, a resistor, right? We've learned about some of these before, and then I might have a voltmeter, and then I might have a power supply. Notice the power supply is like a series of lines, something like such and such, right? But this right here, that's the capacitor. But now when we talk about a capacitor, capacitors can be in parallel or in series. So here we have an example of a capacitor that is in parallel. Now here's something interesting. When you're trying to figure out what the total capacitance of the system is, how do you calculate it? When it's in parallel, here's a weird deal. It's going to be weird. When it's in parallel, what you do is you add up the capacitances. So the total capacitance, QEQ, would be equal to, or not Q, C, EQ, is equal to C1 plus C2 plus C3. Now realize that that's kind of backwards of what we do with resistors. Resistors, that's what the equation looks like when it's done in series, right? So this QEQ is equal to whatever 1 plus 2 plus 3 is. It's actually backwards. And when you do it in series, it's also backwards. So here's what we have. Two capacitors. One at C1 is 12 microfarads. The other is unknown capacitance. So all right, let's talk about how we want to do this problem here. I need to draw the circuit diagram. All right, so they're in parallel across a battery with an EMF of 9 volts. All right, so I'm going to draw my battery, right? And I'll say 9 volts. And if they're in parallel, right, we've got this one, and we've got this one, right? And we know that one of them has a capacitance of 12 microfarads. All right. Now, if you look at the question here, what is the value of the capacitance of C2? We're going to call this C2. So that's the question we're trying to solve. Now, how are we going to do that? Now, you got 9 volts. Now, what you have to do is you have to realize there's an equation that we learned earlier, and that is U is equal to 1/2 C equivalence times V squared, where U is the energy, right? So U is like the joules. It's like 1/2 mV squared in the sort of physical world, and it's going to be 1/2 times the capacitance times V squared volt, not squared, not sub 2. All right, and we can solve first of all for the equivalent. So what do we know here? We can say, and of course the U is the energy, right? And that's the 0.15. So I'm going to put this into my equation, right? I'm going to say 0.0115 joules is equal to 1/2 times CEQ times the voltage, and the voltage was 9 volts, so 9 squared. So I get my calculator out right here. So 9 squared is 81. So 81 divided by 2 is 40.5. So this is 40.5 times CEQ equals 0.015115 joules. I'll divide both sides by 40.5, right? So 0.0115 divided by 40.5 gives me 2.84 times 10 to the minus 4th Faradays. Now, as you recall, we like to sometimes do things in microfarads. This is a microfaraday, and if you want to go from Faradays to microfarads, you would multiply it by 1,000,000, right? If you want to recall there, you would say 1 Faraday is 10 to the 6th microfarads. So I'm just going to take my number and multiply it by 1,000,000 times 1e6. and I get 284. Yeah, 284 microfarads. Now wait. That's the equivalent, because ultimately we've got CEQ is equal to C1 plus C2, but we know that C1 is 12, right? And if this now number is 284, we're going to take 284 minus 12. So on my calculator, I subtract those numbers, and I get it to be 271 microfarads. That's the answer for the C2 right here, which is the answer to the question. Make sense? Now let's talk about what happens when we have capacitors in series. You probably have written this ticket here. The trick, of course, is it's the same thing. It's opposite, right? It's like of resistors. So when you're writing out the equation, you can say 1 over CEQ is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So it's backwards from parallel circuits. So here we have an example right here. So here we have a 3 capacitors in series, and the voltage will be the same drop across all of them. Then you have to add them up in that kind of inverse way that we do. So if you're trying to figure out what CEQ is, right, we would use that equation that I just printed on the previous screen. So let's do an example right here. We consider the circuits in this sketch. We've got a 12-volt battery, so this is 12 volts, and 3 capacitors connected partly in series, All right, the equivalence passage is, so if I answer 2 questions. What's the capacitance, and what's the total energy stored? All right, so how are we going to do that? So first of all, we've got to add up. We've got 2 in series, and then this batch also in parallel with this one. So I need to take, I'm going to call this 1 over C1. We're going to call this C1, and I'm going to call this C2. Does that make sense? These combined guys. That's going to be equal to 1 over 10 plus 1 over 5. And I can do that sort of in my head. 1 over 10th plus 2 over 10 equals 3 over 10. Does that make sense? And then the inverse of 3 over 10, or 10 over 3 I should say, because if you flip the bugger around, it's 10 divided by 3. So it's going to be 3.33, right? So this C1, so C1 is 10 over 3, which is 3.33. All right? So the total capacitance, now we have a parallel circuit where this is 3.3, and this, of course, is 20. And then now the total capacitance, CEQ, will be equal to 3.3 plus 20, 2, which is 23.3. Okay? And that's going to be in microfarads. Now, that's question A. We're looking at question B. What's the total energy of the system? Well, remember, energy is this equation U equals 1/2 times C times the voltage squared. So we're just going to plug this in. 1/2 times the capacitance, which is the number we calculated here, 23.3, times 10 to the minus 6th, because that's in microcoulombs, times the voltage, which was 12, I think. Yeah, 12 right here. 12 squared. So watch how I do this, or listen how I do this. I'm going to take 0.5 for the half, right, times 23.3. Now I'm pushing right here on my calculator right here, the double E button, right, E, and then I'm going to say minus 6th times 12 squared. And I get U to be 0.0016 joules. And that's the answer. So folks, these aren't really that difficult. It's really opposites of how you do resistive programs, and I think you're going to figure this out because you guys are smart kids. We'll see you in class.